not that long ago, as careers go, I was invited to begin working on what can really be done with nuclear explosives to divert asteroids should we detect one. And the talks that you're going to see here, I say talks because the nuclear part of it was actually presented recently at a conference in Washington, D.C. on planetary defense, but that was to a bunch of folks that were well integrated into the community, so it didn't have the introduction that you would give to a more popular group. And it's going to focus on the use of nuclear explosives to divert things. Now, I can chat with you or answer questions about some of the other approaches, but this one will focus, when we get to the part on how you would divert them, on the value of nuclear explosives for this. First off, the broad introduction says these things actually hit the Earth. Very rarely you have large craters. This is one that's over a couple hundred kilometers in diameter, definitely at the upper end of what we see. Most of those, fortunately, are a long, long ways in the past. One of them was only 65 million years in the past that left a crater about this big, the famous Chicxulub crater down in Mexico. And there's, again, lots of recognized craters, and many of them only recently recognized. There are things like this central uplift in Texas that's right here that was believed to be a volcanic intrusion back when I used to drive through there. They now drilled down below and said, well, what's all this shock breccia and no volcanic intrusion? So they are recognizing craters that they didn't know about before. And again, the older ones, unless they're very large, tend to be gone. Now, there are also, and was part of this conference we were at, programs for trying to detect the bodies that in fact do pass near the Earth, so that we can get out of the game of playing statistics and saying, well, one's going to hit us any million years now that we don't like, and try to actually forecast a little bit on our safety or lack thereof. Most of the current projects were funded after 1998, when NASA set a goal of discovering all the bodies that are 1 kilometer or larger that are Earth crossing within, to try to detect 90% of them. Now, those of you who actually do, looking for things and try and detect them know that it's very seldom that you can observe 100% of everything, and so it will be very hard to go much past 90%. Right now they estimate, given the decrease in the discovery rate of these large bodies, that they're in fact about 70% of the way to discovering it, and that there will ultimately prove to be in the neighborhood of 1,000 1 kilometer or larger bodies. More recently, however, NASA, let me back up here. NASA decided that, in fact, we should do better than that, because while a 1 kilometer body is a real mess when it hits, a simple 200-meter body would actually spoil your whole day on the west coast of the US. And so they said, well, maybe we should look for smaller bodies. NASA's looking into how to do that. Right now, they have 3 approaches that they're studying. One would be to join with the Pan-STARRS effort of the Air Force to look for faint things out in space. Another would be to join with the LSST, which is a project that the National Science Foundation is funding, and it's not fully funded yet, but it would work somewhat faster. So they're looking at either replicating these systems or building their own. And then, of course, they also are looking at the desirability of an infrared telescope orbiting in the Venus area, looking outwards as a possibility. It is the most expensive possibility, but that depends on how people feel about what we should be doing with NASA missions. This is a set of slides I borrowed from Don Yeomans, and it said, back in 1800, this is what we knew about the inner solar system. And you have the planets. By 1900, we started to discover that this region outside of Mars and inside of Jupiter was populated by smaller bodies, which originally were called planets, and then somewhere, I think around 1850 or 60, they had a conference and decided, well, we can't call them planets, they're too small. Some of them get up to a few hundred kilometers across, but they aren't like the planets that we know. And people keep looking. By 1950, the density's higher. You're beginning to see some red things there. Those are the bodies that in fact have orbits that don't keep themselves out here in the asteroid belt, but in fact come in and cross the Earth's orbit. And, you know, people don't stop looking. So by 1990, you've got this. 1999, you've got more. And then they started looking hard. And so today, this is what we have. And you can see it's kind of getting crowded. They have now 350,000 known bodies. There's about 4,500 objects that are called NEOs, near-Earth objects. And these are objects that probably originated in the asteroid belt. But after some discussion out there with another body, either getting too near Jupiter or running into another asteroid, they lost energy and came in, so they orbit in the inner solar system. Now, those bodies that have that one interaction will have very eccentric orbits that bring them back out to the asteroid belt, and then they come in again. What happens frequently in the inner solar system is they pass by a planet like the Earth or Venus, they get perturbed gravitationally, and then they have orbits that are more circular in the inner solar system. And what they hope to find with this LSST scale telescope, or whatever NASA ultimately decides to do, is they'll come up with 100,000 or more NEOs instead of 4,500, and over 20,000 PHOs. PHO is just a subset of NEO, potentially hazardous object. And the PHOs are ones that come within a 20th of an astronomical unit of the Earth. An astronomical unit is a distance from the Sun to the Earth. And so the things that, in fact, their orbits not only happen to cross the Earth's orbit, but they come within a 20th of an astronomical unit of the Earth, are called potentially hazardous. And so we expect by 2020 to be up to something like 20,000 of these objects instead of the 800 and some that we are today. And when an object is Earth crossing, it's really a 3D problem. And most of the time, the orbit isn't actually intersecting the Earth's orbit because it's tilted. And so it's only when the orbit, as it precesses, you get intersections as the orbit precesses and climbs up, part of it climbs up and climbs down, that you get actual intersections. And the PHOs are the ones that are near an intersection, and they're close enough to an intersection that the time scale for a gravitational perturbation to pull it down and make it an intersecting orbit is short. And so those are the ones that they figure we should keep an eye on those. And you can follow through the dynamics of orbits and use that to give yourself a way of estimating, well, if I see a certain population of bodies, and they've got these range of eccentricities and range of semi-major axes, and I look at that and can work out for the precession rates, well, how much time, on average, is a body spending as a dangerous object where it might interact? And this is the way that they go from the populations that they observe, either with these small telescopes or in the future with larger ones, and say, well, what fraction of those are going to impact? And so if you have a population of 1,000, which is, as I say, what they estimate the 1 kilometer and above size bodies are, the answer is, why, a couple of them hit you every million years. Don't worry. There are currently no really, really big, a kilometer-sized body hitting the Earth is going to be tremendously unpleasant to civilization. A 10-kilometer-sized body, you're beginning to talk about the dinosaur killer scale models, and that is going to be challenging to survive. And there are no 10-kilometer-sized objects in this NEO population at the moment. The survey, as I say, is incomplete with about 700 moderate asteroids known, and they expect it'll be complete to the 90% level sometime next year. When you take the things they're observing with a telescope and put in the estimates of, well, how frequently they'll impact, you get the numbers down here. You also have observations that tell you about the smaller bodies that, in fact, are hitting the Earth every year. And the green triangles here are infrasound measurements of These are just low frequency pressure waves that rattle around for long distances. And the black dots, in fact, are from the DoD satellites that look down, and within some time they will let you know that there was a big bright flash over this area. Don't worry, the signal was not the signal of a nuclear explosive. Then they hand it to the asteroid people and say, maybe you're interested in that. If you look at these, if you look at these black dots, you see, well, they're getting up to things happening every some number of years. Okay, this is the 1-year level. This is the 10-year level here. And you're getting up to over 10 kilotons of energy that they have observed dissipating. So this is the impact rates, and I put it on a logarithmic timeline. Logarithmic timelines are really great for putting on things that go back to the dinosaurs and start at short periods. So on this timeline, this is the duration of the conference we were just at. This is a congressional term, and every congressional term, there is an 8 to 10. Every year, there's over a kiloton event that happens in the atmosphere, and there's an 8 to 10 kiloton one every congressional term. Now, the thing about 8 to 10 kiloton ones, unless that 10-meter body was an iron nickel, which is only about a 20th of the number of meteorites that we find, unless that iron nickel was rock was iron nickel, it doesn't reach the surface. And rocks, especially if the thing is unconsolidated, so it's just a bunch of rocks that are hanging together, maybe loosely bound, but it comes apart in the upper atmosphere. And so these 8 to 10 kiloton events are happening up at 30 kilometers. Now, if one happened over San Francisco, people might hear something and wonder, where's the thunderstorm and the big bright flash that occurred outside, but it's not going to be devastating. There was a circumstance in these studies a couple years back where a body that was about 30 meters across was discovered, and it was discovered after it had passed very close to the Earth. I mean, inside of the orbit of the moon, well inside of the orbit of the moon. And in fact, there was a period when they said, God, that could have hit us. And the press went out and spoke to the usual suspects about, well, what would have happened if this 30-meter object hit us? A lot of energy, 10 megatons, but it's still at the 30-meter size, thought to be something that will break up in the atmosphere and not make it right to the Earth's surface. You start making it to the Earth's surface at the 50-meter range, on average, they think, as long as you're not iron nickel. Okay, iron nickel, splat. Okay, so fortunately, those are the most common things, and they occur. They deposit their energy high up. Not a severe problem to have to go and address. Things do make it to the Earth's surface on occasion. You'll all know about Tunguska. When I made this slide, Tunguska was thought to be about a 10 megaton event. It knocked down forest in about 2,000 square kilometers, and it was probably unpleasant to be there at the time. The Tunguska event was, at the last conference, downgraded by detailed calculations and looking at the actual health of the forest more correctly. And they think, oh, it was only, 6 or 7 megatons, not 10. That makes them a little more common than was estimated. Those things are thought to be 500, 1,000, 2,000 years. That's the time scales you have those on. Those clearly do have an impact. And as the humanity spreads across the Earth and fills it, this type of thing will become more problematic in the future. And this is just showing what happens if you get a 1,000 megaton event up here, and it occurs sort of in central California. And I looked at the 10 psi level and the 40 calorie per square centimeter flux level. That's the inside of that circle, which includes LA, San Francisco, Sacramento, and Carson City. Everything is knocked down, and terrain effects will shield you on the other side of the Sierra, I'm sure. It's knocked down and burned inside of that region. But fortunately, again, that's a relatively infrequent thing, getting out to the 100,000 year frequency range. Well, we're out there observing these guys, and how long do you have to observe them before you know it's going to hit you? And if you look at the data on asteroids that have been discovered recently and how precisely they know things like the semi-major axis, so how precisely they know the period, you can start doing estimates on how much observation do you need, how many orbits do you need to observe before you know its position along its orbit to better than an Earth radius sometime in the future. And it turns out you need about 10 orbits. Okay? So after about 10 orbits, which, you know, for things that are in the inner solar system, so their scale of their period's about a year. So after about 10 years, if gravity's the only thing going, you can generally know where these guys are going to hit, whether they're a threat or not, inside of 10 years of having detected them. But unfortunately, gravity isn't the only thing going. Now, one of the things people have brought out for asteroids is light. And one fellow even proposed painting an asteroid white that was going to hit us. And you know, some year in the future, if you paint it white, the reflectivity is different. So there's the momentum from sunlight bouncing off of it instead of getting absorbed. That momentum difference has an effect over time. But if you took the 250 tons of paint that it would take to cover a 1 kilometer asteroid, you'd do much better to just impact it on the asteroid than actually paint the asteroid. You know, maybe use a paintball gun. But you'll do more by using the paintball gun than you will by getting the light on it. Okay. Also, it works. Nominally, it's the type of thing that can work in some centuries for a small asteroid. It doesn't work so well for a large asteroid. We can go into the physics later if you like. Just take my word for it now. Nature doesn't stop there. There's the Yarkovsky effect, and that's a way to weed out people who actually look at the field as opposed to don't look at it, because when you start naming effects, oh yes, the Yarkovsky effect. It's an effect where that light that comes in is absorbed by the asteroid. Now, the asteroid, like the Earth, is in a thermal balance, so the light that comes in and gets absorbed has to get re-radiated off, and it's in balance. Now, if the asteroid, almost all asteroids are rotating, and so if the asteroid is rotating, the sunset terminator, if you will, on the asteroid, is often hotter than the sunrise terminator. How much hotter depends on the direction of rotation and the material properties of the surface. If the surface is iron nickel, has good conductivity, and the energy that's absorbed at the surface gets conducted deep in the material, and the temperature is not very different over, say, a 4-hour rotation period. And so it re-radiates the light off evenly in all directions. But if the surface is sandy, now those of you who've stood out on your volleyball court in the middle of the summer and got your shoes off, discover that the surface of the sand can get quite warm. It's poor conductor. And so if you have a surface that is lots of small stuff and poor conductor, the sunset terminator is hotter than the sunrise terminator. This gives you a rocket effect because the momentum of the photons that you emit at the sunset terminator dominate and push you preferentially in the direction that matters, that is set by, well, your surface material properties and the rotation properties of the asteroid. Now, as an example of how this adds up, there's DA 1950, which was discovered in 1950, was lost because a lot of the things that people discovered in 1950, you had a couple of old geezers that went, people my age, who went out to a telescope at that time and had a 2-week run at the telescope, spotted an asteroid, picked it up, calculated its orbit. I did my first orbit in 1969, calculated its orbit, and then if they didn't get out to observe it again in the next months to years, the initial orbit they calculated may not be good enough to re-pick it up. So DA 1950 was one of the ones that was lost. It was serendipitously rediscovered as it passed within a 20th of an astronomical unit of the Earth in 2001, yes, 2001. And when they do the orbit, they say the collision probability on Saturday, the 16th of March, 2880, is no greater than 1/3%. Okay? So That, by the way, is by far the worst one that you've got out there that we know about. And at JPL, they looked at all sorts of uncertainties in their calculation. This is one of the best studies that I've found on the uncertainties. And so, well, how much does it change things if you fiddle around with the solar oblateness? This is the interior rotation speed of the sun that the general relativistic precession of the orbit, perihelion of Mercury's orbit is based on. And well, it switches it somewhere between, depending on how you play with it, 2 to 6 Earth radii. The difference between a hit and a miss by a lot, okay? You add 61 asteroids to your calculation. It shifts it the other way by 230 Earth radii. You put in planetary mass uncertainties. When this guy's coming out, he periodically passes not very close, but close to other planets. And there's always a gravitational tug. And the masses of the planets are not certain precisely. They're pretty well known now that we've put satellites out around them. But that adds greater uncertainty. Radiation pressure, just the straight one I mentioned first time of just the light bouncing off of it and how efficient that is, that changes the calculation by 1,700 Earth radii. The Yarkovsky effect, how much does that change things? Anywhere between plus 1,800 and minus 11,000, depending on how the surface properties that we don't know without going there. Okay, so it's real hard to know where a body's going to be, even when you have really great observational data. I mean, if it weren't for the effects of light, it would, you know, if it weren't for the effects of light, well, we'd be kind of close to saying this is a real threatening body 800 years out. But, you know, with the light, it's sort of hopeless. Another body that was picked out by the Sentry system that's run, and here what they're doing is they're taking all of these asteroids that you saw and doing orbits for them, and they're looking for potential impacts over the next 100 years. And they're limiting themselves to the next 100 years because when you get beyond that, these non-gravitational effects start becoming dominant, and even the gravitational effects, uncertainties and masses, become a problem. Okay? And so this is listed today, or it's listed in the JPL site as a 270-meter object. More recent observations suggest it's really closer to 350, but you know, I stuck with what JPL was saying. And at first when they saw it, they thought there was going to be a possible collision in 2029. They were able to look backwards at earlier observations that they hadn't recognized it in. They said, oh, you know, if we take this orbit and go backwards, here's a field of view that we actually have an earlier image from, and we'll pick it up there. And they were able to very quickly improve the orbit. They know it's not going to hit in 2029, and that there is a remote chance of 1 in 45,000 that it will impact the Earth on 2036. That means 99.998% certain it won't, which is, you know, not going to worry too much right now. If you take the 120 asteroids that they put in their risk table and you add up the cumulative probability of an impact in the next 100 years, it comes out to about 1%. But most of that is for bodies below about 10 meters. Bodies that they don't normally discover except when they whiz past the Earth very close in. Okay? And also bodies that you probably wouldn't do anything about even if you knew it was going to hit, except tell people to look at the light show. So, so most of those bodies are small that lead to that 1%. If you consider only the 38 of the 120 that are larger than 50 meters in diameter and large enough to impact the ground, they have a cumulative probability of 1/50% in the next 100 years. Again, not anything to worry about tremendously, but we're going to have to learn to communicate better about this risk because in 2020 you expect to have 20 times more of these objects. So that says 20% chance in the next 100 years you'll say there's a 20% chance this guy's going to hit, and you'll probably actually then gather more data on him to know. And even the big ones are beginning to have there's beginning to be a chance that you'll see something that you begin to really worry about as a threat. Okay, so when we have identified something that might be a threat in the future, the first thing is do no harm. So as we've described it, it's easy in the next millennium to know an object in the next millennium or so is not going to be a threat. You look at its orbit, it doesn't pass anywhere near the Earth. Okay? The problem are those guys that have orbits that are nearly intersecting, that can precess in a limited amount of time. But when you look at those guys, because of all the uncertainty caused by light effects principally, but also by uncertainties in planetary masses, it's difficult to know that a body will impact more than a century, or a few decades really, in the future. When the JPL people did their study, they limited themselves to 50 years. They said, look, inside of 50 years, give us 10 orbits or so, and we'll know it's going to hit or not. But so it's difficult to know something will impact more than a century in advance. And when you have bodies like Apophis, which are not uncommon, the orbit is such that we won't know, or there's a chance we will know it won't impact earlier than 7 years in advance, but we will not know it will impact until about 7 years in advance, unless we fund a space mission, something like that, to go out and put a transponder on it so we can actually get more precision in the orbit. So mitigation technologies, you don't think about ones that work in the centuries ballpark, where you say, oh, well, DA 1950 may be a problem 800 years out. If you go out and start pushing DA 1980, the chances are you'd push it to one that it's not going to impact. Chances are best that it's not going to impact. You start changing it, well, maybe you change it to something that does impact. So do no harm until you know that a thing is going to impact. Okay, now the options I'm going to talk about today are the nuclear option for diverting it. As I said, if you afterwards wanted to ask questions about some of the other proposals, I'm happy to chat about them. NASA just released a report to Congress on what it would do to detect and deflect NEOs. And basically, it said that, look, for large asteroids, the only thing we have today that is mature technology that we know would work would be nukes. For smaller bodies, they think that impactors, where you just take a mass up and run it into the body real hard. And so for smaller asteroids, that can work. They place the gravity tractor, which gets a lot of press coverage. They place that as, well, a medium thing. The nuclear and impactor was high likelihood of working. The the gravity tractor was in the medium category as something that could be developed to a workable technology. Anyway, there are two ways that have been proposed to use nukes. One is to just try and tap it. And the idea is when you're some decades out, the velocity change that is the difference between a body that hits you and a body that misses you is in the centimeters per second range. And so, if you can go out and you can do something to just tap it enough to change its speed by a centimeter or two a second, that's what you want to do. Okay, and you keep the body together that way, and good. The alternative is to blow the bejesus out of it. Now that method, while intrinsically satisfying to an old bomber, has the problem that what it creates is a debris field. Now, if you create that debris field, what was it in Deep Impact, 18 days before? If you create the debris field shortly before impact, don't bother. It's a effectless thing. If you create it, however, some years out, so this operates decades out, but if, as in the case of Apophis, let's assume that we don't have a space mission to put a transponder on it to know for sure that the small probability of it hitting is the bad case. In that case, we're not going to know until 7 years out. It's not just a little tap anymore that you need to do. However, if you do this, what we'll show you is if you do this a few years out, in fact, you create a debris field. Now, then you have the choice. Do you want the whole body to hit you, or do you want 100,000th of the body to hit you? Probably in things mostly that burn up in the atmosphere. So that's not the desirable case. You don't go volunteering to put the Earth in a place where you don't move the Earth so that you can have this occur. But it's something that you can do if there's not another option. If 20 years out or 30 years out, you tapped it and it didn't work. And you can't there are launch windows for these things. And so an asteroid that we discover 30 years out and say we got to do something about that, you may only have 4 launch windows when you can reach it in that 30-year period. And so you got to do something early. And if that's something that you do early doesn't work, the time gets short real fast. Okay. So whereas I heard Dave Morrison, who we actually invited to come here with us, but when he wanted to come at first, but when he heard the day, he said, "Sorry, I'm traveling that day." I heard him on NPR recently saying, in response to, "Well, would you blow it up?" He said, "No, that's bad because the stuff will still hit you." He's absolutely right. But again, I think there's a real environmental improvement to reduce the amount that hits you by a factor of 100,000. So that's what we're going to talk about. How do you nudge an asteroid? Well, first of all, there's this tyrant Newton, and he says what you got to do is there's the action-reaction. And so if you're going to ablate off some material with a certain velocity, there's the mass of the asteroid and how much speed, how much its velocity changes. And what it says is, well, if you're going to heat that surface to just a low temperature gas, a 1 eV gas, it's about 10,000 degrees. So you heat a hemisphere by standing off and just heating it up and blow off a part in 10 to the -5 or part in 10 to the -4, depending on how many centimeters a second you want to change things. Well, what that says is I've got to heat 10,000 to 100,000 tons of material to a gas. Okay? That's a tiny fraction of the mass of the asteroid. And that's what you need to do to change its speed by 1 to 10 centimeters a second. And the energy required to heat that material, the energy I have to couple in, is somewhere between 10 and 100 kilotons of energy. Now, it doesn't matter if I'm doing this by a nuclear explosive that I've hovered some distance off of the surface, or if I'm doing it with a big laser that is somewhere in space so it can actually focus at this distance and trying to heat the surface. By the way, at Livermore, we have the largest laser in the world, the NIF, and we can get this much energy through at the 10 kilotons in about 6,000 years. It's not designed for high fluence, it's designed for really intense pulses. So it's not a fair limitation on lasers. But lasers, you're talking pumping 10 to 100 kilotons through it. People say particle beams, 10 to 100 kilotons through it. People talk about putting giant mirrors and orbiting around the asteroid. Okay? And so you take a mirror and you keep the mirror hovering off the asteroid at the right distance because there are no close-in stable orbits, because the asteroids tend to be unusual in shape. And so you're actively controlling your mirror and pointing it probably to a secondary that's much closer in, a secondary mirror, and reflecting onto a spot on a rotating surface and trying to get that spot hot enough before, in spite of the rotation, that you cause it to outgas. Now, using free sunlight, if you've got a mirror that's, say, 70, 80 meters across and optically good, it will work, but you need to have the mirror standing back and the secondary in close to do the steering, because the rock that you evaporate and come off goes out and coats the optics real quick. And so these things are all things people think about, but the real issue is however you're going to move it, you're talking about this much energy. Okay? Up, go back one. Now, at this point, it's illegal for me to say, and Steve and Rob, what yield weapons we have in the stockpile. It's against the law. We'll be put in jail and never let out. However, there is nothing to stop me from saying the Russians have developed things that this was their Tsar bomb, the 100 megaton one that they tested at the 50, 60 megaton level back in the 60s. There's Edward Teller sort of petting it at Chelyabinsk 70. And this is the 1.4 megaton Starfish Prime event over Johnson Island that the US did. And it suggests we know how to get nukes into space, and we know how to get them up there and megatonish things, okay? That much I can say about what we have in the stockpile. If you want to know more, I cannot recommend you're going to these proliferant sites like the NRDC or American Federation of Scientists, where they list a lot more than we're allowed to say. So Livermore, where we work, is experienced in both making craters and modeling craters. And this is a crater created by RV impact. I go out and do that in the South Pacific every so often. Went out just before the asteroid meeting, going out again, I think in June. This is the Sedan crater. At this scale, you don't see all the car tires down at the bottom of it where people had rolled them down just to watch them try and spin them around the rim of the crater. I have to speed up here. And the computation we're doing was with a 2D code. We have 3D codes. This is showing you a 3D astrophysics calculation that I'm particularly happy with because we solved a 30-year-long problem on CNO abundances in red giants. But 3D shape adds complexity that were unnecessary for scoping calculations to try and learn more about what modeling should be. And a sphere can be run in 2 dimensions, and so you get better resolution. To get the if you had 100,000 zones in a 2D calculation of a sphere, to get the same resolution, you need 300 million zones in a 3D calculation. We are capable of doing that, but it's not the first calculation you should do. And you do it later. And so Kale was the code of choice in this case, and Steve over here was running Kale, and Rob was running Steve. And just to give you a real quick thing, because we got to get through this fast. Kale's an arbitrary Lagrangian Eulerian code. It's 2D, has lots of physics in it. This is some old calculations Steve did of a Leonid meteorite impacting satellite skin. Get real high temperatures when it impacts at 70 kilometers a second. The generic structure that we chose, and this is part of the greatest uncertainty in what asteroids are like. Again, asteroids are almost none of them spherical, but we're starting there. We chose a kilometer radius just because in the NASA study, when you get to about a kilometer, suddenly the threat pops up high because they start saying, well, we know there's going to be global effects there. We don't know in detail what the global effects are, but you're going to impact more people. And the idea is if you have one of these events in 1 million years that kills 1 billion people, that's 1,000 people a year. And so they knew that somewhere up there where the global effects start in, and it's about a kilometer, life got real bad. Our model had, it was really a sand-like material on the outer half of the radius and a granite-like density at the inner half. And we looked at 2 energy deposition modes, one where it was deposited just 10 meters below the surface, you know, just getting it under the surface. And you can do that with Earth penetrator approach. You just sort of run the thing into it at a few thousand foot a second, and especially on things like this, it'll bury itself that deep. Alternatively, you stand off about here, and you irradiate the surface, about here, I guess, and you irradiate the surface, and you heat a big patch on it. Now, we ran some of these. I'll get to that, I guess. And this is the zoning that was used, and radiation transport was turned off because that really would be critical, the key issue, if you were standing off and irradiating the surface and looking at the energy transport into the surface. We just said, oh, we've done that type of thing before. We'll put it in about here and put in a certain number of kilotons. Okay, the real issue is we don't have we have strength and fracture models for Nevada alluvium. There's some beautiful work done for limestones from the Midwest somewhere where you get different porosities, and shocks propagate quite differently in a stone that's really hard or has a really low porosity. And we don't know about asteroids, and in fact asteroids are probably different. There's probably some that are pretty hard. That DA 1950, they're now thinking it's a nickel iron. But before we knew that, we knew its density was at least about 2.8 or 2.9, which would make it pretty solid rock. Okay, so those are the things we have to vary. As to strength, there is a cutoff at about 2 hours where very few asteroids are seen to be rotating faster than 2 hours. And that's an interesting cutoff because below 2 hours, the gravity of a body will typically hold it together. And so the fact that most of the bodies that you see with 2 hour or longer periods just don't exist as short period objects suggests that most of the bodies you see are held together with gravity. It doesn't mean they don't have some big honking pieces in them, but it means they're mostly held together with gravity. This is a picture of Itokawa from the recent Japanese mission Hayabusa that went out and looked at it. That's about 80 meters across, that rock. down there. There are some bodies, including quite sizable ones, that are rotating so fast they have to have material strength holding them together. So there's variation out there, but on average, the bodies are likely to be rubble piles, maybe with some big pieces in them, that don't have a lot of material strength. So we will do calculations with material strength and without it. Okay? We're not going to show all of them here because they've only just finished some of them and I couldn't get them into the talk in time. The other question is, which direction do you push? I don't have time to talk about that. I see I'm cruising up. But generally, everyone knows you push in the direction of motion or against the direction of motion to get the best effect. And the reason for that is when you push along that direction, you're changing the period. And so if you do it one period out, you get the effect of one period change in its position. If you do it 2 periods out, you get the effect of 2 periods change in its direction. So the miss grows with time. And if you do it in the other direction, you may do it hard enough to get a miss, but it doesn't grow with time. You know, either you did it or you didn't. And the miss will be close in the other directions. There are times when that's the right answer, but only very late in the game is that the right answer. Okay, where phase matters. So pushing at perihelion for an eccentric orbit is much better than pushing at aphelion. And that's the ratio. Perihelion push is preferred. We'll go on from there. These are the orbits. When we do these calculations, we have to propagate them along orbits and say, well, how does the debris field evolve? Or if I nudge it, how does that nudge evolve with time so that I miss or not? What do I have to do to stop it from hitting if I'm nudging? How does the debris field evolve with time if I have to break it up and I'm flying through that debris field? What am I likely to run into statistically? And we picked 4 orbits. The 4 orbits are the blue dots there. They lie amidst the NEOs that we know about. 2 of the orbits had low angles of inclination. What you'll see on this is the distribution is that things with low angles of inclination are things that are accidents waiting to happen. The things that have low angles of inclination, preferentially the orbits are better aligned with the Earth's orbit when they cross, and so the length over which an impact may occur is greater. And so these things get swept out faster. Basically, over time, all of these bodies will either impact one of the planets or get gravitationally boosted out of the system. Most of them will impact one of the planets with time. It fortunately just takes a long time. Okay, we're going to use megaton class devices to nudge things. This shows you a picture of Bikini using a Google map or photo. This is the Castle Bravo event that was done on a little island about here, and it was placed 9 foot above water level and set off. It was 15 megatons, and it created a hole this size. The 1 kilometer asteroid that we're nominally modeling is this size. Okay, these are the orbits. As I say, 1 through 3 cross at a great angle. Orbit 4 that I picked is a real bugger. And it's a bugger for anything you want to pick. It's the one that I showed at first, and what happens is it's going around and it really comes tangent to the Earth's orbit and sort of an osculating orbit. And so what happens is, in the wrong phase, it gets into the Earth's orbit and the Earth overtakes it. So it's the least energetic hit, but it's much like the Shoemaker-Levy orbit was for Jupiter, and it's a hard one to, if you discover something on this path, it's hard to avoid. For orbits 1, 2, 3, perihelion perturbations at perihelion of 5 centimeters a second are adequate 3 years in advance. Barely. If you go 30 years in advance, 0.5 centimeter a second is all you need. So that's the reason that you really want this timeline where you say, okay, 50 years to go, let's start doing something, because the amount that you have to do is greatly reduced. And you need to only take this guy and nudge him and get of order 1 centimeter a second, or 0.5 centimeter in a second in these cases, to grow. Orbit 4, if you do it 3 years in advance and do in the t direction, it requires 3 meters a second velocity change. Well, on an object that has an escape velocity of 50 centimeters a second, you've got to break it up to you're not going to get that kind of change without breaking it up. Still required half a meter a second in the opposite direction. 25 years out, it still requires 5 centimeters a second to cause a miss. And this doesn't show very well, but it's looking at the evolution of the debris field with time. And the scale across here is 3,000 Earth radii. So over a period of 3 years, you grow to a thing that's nearly 2,000 Earth radii long. A debris field is 2,000 Earth radii long, and 50 to 80 Earth radii across. Okay? So it's got a volume that's more than 1 million times the volume of the Earth. When the Earth passes through that, it picks up some of that material. But the amount it picks up is in the neighborhood of 10 to the minus 4th or 10 to the minus 5th of the material. So again, last minute, 3 years out or so, this is the type of thing you would be forced towards. Okay, Model A. And here you see Rob's movie, or is that Steve's movie? I don't remember. One of these guys' movie going off. And you see this crater forming and the density going down. After 20 seconds, the granite area was here. The outer rubble area looked like that. 77% of the material had been thrown out, of the problem. Just when the burst went off, material recoils off the asteroid as the shock penetrates into it, and it went out at such a high speed it just left the problem. It couldn't track it. 92% of the material still in the problem. For those of you who are aficionados of the virial theorem, if you look at the kinetic energy to potential energy ratio, the core is 300 and the mantle is 1200. For a stable body, if it were a gas body, you'd want a half for it to hang together. Anything over 1 comes apart. So this thing is coming apart. Not everything impacts. In fact, the body was going along an orbit where it's going to hit. And so if you speed it up a little bit or slow it down enough, it's not going to hit. So the only things that actually hit are the pieces of this material. This is the thing being tumbled around in about a 28,000. We did sort of 750,000 fragments in this on one of the runs, and this is 28,000 of them, but it shows the general shape. But the stuff that's going like a bat out of hell one way and is 2 meters a second slow has a chance of impacting. The stuff that goes like a bat out of hell the other way, but and is sped up by only 2 meters a second in the direction of motion, can impact the other way. But most of that material misses by of order 100 Earth radii. Just doesn't come close to the Earth. This is looking at the stuff that's within 2 meters a second, and it's actually only a strip across that passes near the Earth. And it's this green area where the Earth-threatening material is in this case. The one question is, this was run without material strength, and so it's more fluid-like. There are all sorts of calculations you can do between a full-up rock and something that's fluid-like. And Rob has just done one where he put in more of an equation of state that you would use for beach if you hit it, in the sense that it's got an equation of state where the strength increases as you put pressure on it. And then as the shock passes, there is no tension term. And so things perfectly happily come apart as they would in a powder, but you actually get some strength. In that case, you actually have a line, a very thin plane that goes through the asteroid, but I haven't gotten that one all gizmoed up yet. And there are calculations we can do that develop strength and do it for asteroid materials. And in fact, just recently I found that there was some work being done at Harvard on that, and we're going to go looking at that, where they grind up asteroids and look at the equation of state better. We just grind up Nevada. Okay, so with respect to this method, you pick. These orbits, depending on 1 through 4, range from 112 gigatons to 12 gigatons of impact energy. So you can do that, or if you break it up, you receive somewhere around 10 to the minus 5th of the material, so 10 to the minus 5th of the energy impacting. Or on orbit 4, we could only get it down to 10 to the minus 3. So most of the bodies yeah, it was only when I broke it up into relatively small pieces that I actually started getting significant numbers of impacts. And so while there is a chance from this, this is not the desired method of just nudging it and trying to keep the whole thing together. Most of the bodies will be small that actually hit the Earth. Alternative, use a bigger hammer, use 10 megatons, about a tenth of a Tsar bomb, and you drop things down to 10 to the minus 6 and 10 to the minus 4 for the bad orbit. Going further, what happens if there's a hard rock in the center? Hard rock in the center is the worst place the hard rock could be, because here we actually fractured the rock, and you can still see it in there, but it stayed together, and it stayed on a course that was going to hit the Earth. So knowing the structure is desirable. If this hard rock had been up here, it would have missed, and you'd have had almost the same case that we just had. But this isn't a panacea. Much better to attack things early on. I'm just saying this is what you do if you can't do anything else. This was looking at the thing in the middle, and it was bad. It actually hit. And the alternative here would probably have been, probably you won't send just one. If you've only got one launch window, you might send 2 or 3. And the first one goes to where the thing is. And the second one is following behind, and it goes to where you don't want anything to be. There is the nudge. And we source the energy into a range at a depth that was appropriate for using neutron output. Neutron output is more desirable than X-ray output. If you set up a nuclear weapon off in space, there's almost no mass there. And so most of the energy that you have coming out comes out as radiation of one form or another. It comes out as X-rays, gamma rays, neutrons. And that's what goes out and absorbs on the surface of the asteroid, heats it, and ablates that material off. And when it ablates that material off, you get a push. And here we ablated off about 30,000 tons, so in the right ballpark. This was the speeds. The purple here is stuff that has a speed, pieces that have a speed that can escape. This is escaping, while this temporarily has a speed that would allow it to escape. When you say it's got to push this out of the way, it doesn't have enough energy to push that out of the way. And so this will just form a big crater on the thing. And we got out 0.5 centimeter a second if we had not spalled off of the far end, which is an issue of the dissipation in the material. And so I'm hoping that when we run the powder on this one, I'll see that I don't get as much spall. The powder equation of state on this one, hoping we won't get as much spall, we'd have gotten 1.8 centimeters a second. In either case, that's enough to avoid an impact. If you deposit it more thinly, as you would do if you were having X-rays, it actually gave a stronger shock early on. All of this material escaped. The body was going, 92% of the mass was bound and was going 2.1 centimeters a second. That's an easy miss 20 years out. And you only have a little bit of debris cloud around it. And again, you only pick up a tiny fraction of that. Let your debris cloud grow 30 years instead of 3 years. Okay, so conclusions now, because we're out of time. Conclusions now, it's only natural. There'll be a global disaster any million years now, but 1 million years is a long time. Here you see a skull of Homo heidelbergensis, which we call Los Alamos man, where I work. And, they evolve. The nuclear nudge is the preferred approach. Neutron output has its advantages. There are studies that we're continuing to do to improve our simulations there. With less time, fragmentation you shouldn't take the one-line answers that people give about, oh, fragmentation is bad. Fragmentation is not the preferred way, but there are times when you can say it's better than doing nothing, a lot better than doing nothing. Also, if you want to talk about myths busted, device doesn't have to be at the center. The New York Times wrote, oh, but there's radioactive debris. And I worked out if the radiation actually is spread quite widely that you have left over from it. But let's assume it spreads only as the material of the device. And then 3 years later, when you sweep this material up, your background radiation goes up 0.01% above background from it temporarily. So, you do more getting in an airplane. they're a mature technology. There's more we can do to learn about them. We have active programs, and we'll quit. Thank you very much. And if there's, yes?
Sound like that blowing out and nudging are mutually exclusive methods, but they're not.
Well, the cognitive difference we're talking about here, most of the methods for nudging it actually ablate off some of the material. The alternative that NASA proposed was to say, well, if they're small enough, you instead of taking a spacecraft that weighs about a ton, like a big nuclear package would, I take a package that weighs about 10 tons. And I launch that and I impact it on the body. And there's the momentum that it hits. And there's also, because it's got excess energy, it will throw off some of the body's mass. And so there's always something that comes off of it. The difference between the nudge was we're trying to keep the bulk of the body, more than 90%, hopefully 99% and more of the body as a single object that is now moving at a non-intersecting orbit. So does that answer it? I mean,
what I was thinking is, you're saying that there are these back cases, but what if you hit it in such a way that the explosive will push the back cases away from the orbit as well?
Well, I mean, that's what we were doing. We were taking in one case, trying to gently push on it. That's where the nuclear device was standing off and just irradiating one hemisphere, so that you're trying to take the bulk of the object and push it at a speed just enough to stop it from hitting us. The alternative, again, if you didn't have all of that time, is you hit it very hard. The fragments go out in all directions at high speeds. Some you create a debris field, and some fraction of them the Earth still picks up. But again, your choice is quantitatively different with 100 with the whole thing or a small fraction. Yes.
So I guess I have sort of two questions. One is if you do fragment it, then you end up on the next orbit, some of those fragments may hit you, which
well,
take into account. You're just going to say, well, we're just going to take care of this one, and then we'll figure out what happens on the next part.
You will generally know that. Well, first off, that debris field keeps orbiting or keeps expanding. So you're right. You are taking one object and you're converting it to hundreds of thousands of objects. Now, as I told you early on, there was the, you saw all those objects in the inner solar system. Most of those objects are going to stay there until we hit them. And, in a sense, that's the choice between hitting them hitting them today or hitting some tiny fraction of them 1,000 years in the future. Yeah, you can afterwards look at the debris field and get some idea of how many more orbits before the two again pass near each other. And what you would hope is that, in fact, when the Earth first passes through it, a lot of the stuff that is near the Earth's orbit is going to get gravitationally perturbed so that it's in quite different orbits afterwards. So that is an issue, but that's an issue also if you nudge it. Whatever you do, you're changing the orbit, and it's just not an orbit that's hitting immediately then, and you wait for your great-great-great-great-great-grandchildren to deal with it if they're interested. There was another...
And all these, the people in, Washington, what threats are they looking at beyond just, asteroids or comets?
Oh well, the conference that we were at was very specifically on asteroids, not comets. Those are the, the doggerel about the guy on the stairs who wasn't there, and I wish he weren't there. Comets are those guys. We can't do anything about comets. One of those has our number on it. We hope that the future has better technology.
Why are comets qualitatively different?
Well, comets are qualitatively different because they come from the outer solar system, and they come in only occasionally. And so unlike the NEOs, which are in all the time and we're able to get a census of them, comets, usually it's very unusual that you discover one, say, 2 years before it is going to hit the Earth. And at that point, if you discover it that early, which is very unusual, it's out at Jupiter's orbit. So ask how long it takes to get a spacecraft out there. I mean, if you meet it out beyond Mars's orbit, and it's on its way in to impact us, which you probably can't know because of all the non-gravitational forces. You just know it's going to come uncomfortably close. If you can get out beyond Mars's orbit, you have maybe a worldwide pandemic is a bigger threat than the asteroid. Now, as I say, the asteroid is not a question. It is a certainty, but it's a certainty over some very large time scale. A worldwide pandemic that may kill 1 billion people is thought to be a possibility at a much shorter time scale. So interested in that. They're, from the Homeland Security point of view, they're of course doing exercises to say what would we do if someone got a hold of a nuclear weapon and set it off? What would happen with a chemical attack? And they've got all those listed, and you know, if you look at them, you can sort of assign probabilities, and we're not at the bottom, but we're certainly not at the top. Yes?
I used to do some simple calculations 30 years ago for KMS fusion on their attempt to make ablative effects on a small sphere with
Yes.
in a tritium. Don't you have a little problem in bookkeeping on watching the momentum change due to the spalling off the back surface, canceling a certain amount of the...
And I
That's why years ago I looked at this and I said, the idea of exploding a nuclear device when there's no working fluid around it means that you can't push anything unless you get that heat to do something organized. And the spinning of the planet certainly is efficient in a photon sense. But I mean, I can see uniform body potentially not getting any momentum because there's not much momentum in the nuclear particles. If you look at it, they're extremely...
no. The calculation that I showed for the nudge, the first one, okay, had the exact fact. In fact, if you looked at the title, it said Celestial Newton's Cradle. And a Newton's Cradle is a thing, you know, you've got the little metal balls, and you let one go, and it goes bunk, and a whole bunch of them don't move. One comes off the other end, and bunk, okay? And as I showed, that is in fact what happened at some level. You're right. You're not, with a nuclear weapon, what you're doing is you're putting energy in an asymmetric fashion on it. Okay? Picture a rifle with a bullet in it. Okay? When you do that, the action and reaction are the same when you set off the bullet. Okay? But the velocities are quite different. Okay? And here we're trying to do a thing where we make the side of the asteroid towards us the bullet, or and it comes off fast. Now, as you said, in a fluid system, if there's very little dissipation, the shock can go through and spall the far end off, and I showed that. And I said that with that spalling off, okay, my body was moving 0.5 centimeter a second faster. What remained, because the ablation was higher on one side than the ultimate spall, but that was with a very non-dissipative medium. And with more dissipation, and that's where I said looking at equation of state of asteroid chondritic material would be desirable, because you can then get better idea of how much dissipation you have and have it move. We did the harder hit, and we got 2 centimeters a second, but you know, there we were beginning to lose 6% of the mass, you know, only keeping 93, 94% of the body together. Now, that's still you know, not bad. You know, most of it you're guaranteed is going to miss. And again, 100,000th or a millionth of the 6% now is what may interact with you later. So yes, we do try to account for that, and that is a materials issue in the thing. Okay, and you, yes?
The fragmentation case, I guess this is a question about the density of the debris cloud. Would it take out all the man-made satellites?
You may have noticed that I had a little line on the bottom. I was having to go fast that said, degrades near-Earth environment. What I was forced to take out there was a comment that I had in about, and I would buy stock in the companies that were going to remake the satellites. Yeah, again, it's not the thing that you choose to do. If you discover the things a rational amount of time ahead, you let it, you try and deal with it there. Now, I mean, one of the other issues that we just haven't talked about at all is, what do you do if there's a 100-meter object and it's going to fall someplace that isn't San Diego? And where do you start saying, oh, well, we should do something about that? And especially, we had a section at the conference, you wouldn't believe the liability you take on if you say, oh, well, that's going to reach Costa Rica, and we've got a lot of retirees there. Let's protect Costa Rica. Okay, and when you do it, you know, if you try gravity tractoring it, well, gosh, you see the track point move slowly across the Earth, and you know it gets to you know, Ulaanbaatar, and you say, well, shouldn't we keep using fuel? And you know, probably yes, of course. But you know, and if you do the shattering case, you have something that you think is going to land in the Pacific Ocean, maybe create a tidal wave and wash up on some shores. Well, if you reduce it, you may wind up with a big piece landing in South America or in Europe. And you know, how do you indemnify someone who's trying to be a good Samaritan and convert a major disaster into a lesser one? And those are all interesting issues.
How much of a factor is it between an asteroid rear-ending us or vice versa versus impacting us head-on?
If it's rear-ending or hitting us head-on, you're talking about an orbit. The one that rear-ends us is one that has an orbit that aphelion is well far out and perihelion is in close. And then it's going faster than the Earth, and it will overtake it. The one that you saw, orbit 4 there, had a perihelion in near Venus and aphelion near the Earth, and so it was going slow and we were overtaking it. Neither of those are the really fast cases, okay? In the case where we were overtaking it, it was 10 meters a second was the impact velocity, and in one that overtook us, that was in one of the other orbits, but not exactly coming along the path, it was 15 meters a second. Kilometers a second, sorry, kilometers a second. 3 kilometers a second, by the way, is where material takes on the kinetic energy of high explosive. So 6 kilometers a second, when a thing hits, it's got 4 times the energy of high explosive. And the 20 kilometers a second would be a very typical one of a body that was crossing. 30 kilometers a second is not unheard of. You can get as high as 70 kilometers a second. The Leonids, when they pass the near Earth environment, are crossing it at 70 kilometers a second. And to do that, you need a body that is counter-rotating in the solar system. And the peak speed that you can have at the Earth's orbit is 42 kilometers a second. That's something that has very eccentric orbit and is at its perihelion at the Earth's orbit. So if you have 42 kilometers a second this way and the Earth's 30 kilometers a second this way, that's the absolute maximum you can get. But that's very uncommon. And I don't know if any of the NEOs have that type of orbit. Yes?
As long as we're on this topic of sort of a kinetic energy type thing, has there been any thought about kinetic energy weapons to impact the asteroid?
Well, yeah, except they don't call them weapons then. NASA doesn't do weapons. NASA is interested in bodies that impact the asteroid. The interest there is for the reason that was just mentioned back here, that when that body is hitting, you are guaranteed to get at least the momentum of the body added to the asteroid. Okay? Now, if the body's approaching the asteroid, as it very likely would at 20 kilometers a second, it's not just depositing its energy, it's depositing a lot of energy, and so you have the equivalent of an explosion at the asteroid surface. And that explosion throws some material out this way. Now, how much depends a lot on the porosity of the rock. And a very porous system kind of, you know, is like a catcher's mitt, and the thing comes and it goes, and you don't get a lot of explosion. You're busy, it goes very deep and you're busy sweeping up lots of stuff. That, in the NASA report, it says that right now, at the moment, it would be, for a big asteroid, very difficult to fly something big enough that you would be comfortable that it will do the job. But on a small thing, you could do that. I mean, it would be a more expensive mission than the nuclear one, because again, you'd be wanting a big, massive thing to run into it. But with political sensitivities, some year, hopefully, the Cold War is a distant memory, and people can think about nuclear explosives as a tool that might be usable, as opposed to thinking about them as these terrible weapons and radiation. And in that case, you can come up, you can make a choice differently than we would today, perhaps. But in that case, if kinetic impactors would do the job, I'm absolutely sure that, if they found something that was coming, it was small enough that they could get a kinetic impactor that they were pretty sure would do the job, they would do that first. And the idea being only if it didn't work and time got short would you use a nuke.
At the speeds that you're talking about, though, aren't kinetic impactors at about the same level of number of megatons as the nuke?
No. As I said, the typical number for the speed of approach would be, say, 20 kilometers a second. Okay, let's make it 21 because that three divides into that, okay? So we got 7, okay? And 7 squared is 49. And so pound for pound, if you've got 1 ton of impactor, it's 49, 50. It's 50 tons of explosive equivalent when you impact. So you launch 10 tons instead. Well, now you're talking about 500 tons, half a kiloton. So you've got a choice. I can launch 10 tons of material at it, or a kiloton device. I can't exactly say what it weighs, but I'll tell you, it's a whole lot less. So, and that actually was in the NASA report as a possibility also. We're talking about modeling it, putting little tiny nukes, a bunch of them on the surface, patterning them to try and nudge it that way, as if it were a bunch of impactors, but you're doing it just with carrying a lot less mass. I mean, as long as space travel cares about mass, right now, mass is a real important thing. If you're going to lift it off the Earth's surface, it's expensive to get it into orbit, and then to get it out of orbit is expensive. As long as mass is an issue, nuclear energy carries about 1 million times the energy as chemical. So, the issue is we only know crude ways of using it now. I would hope 100 years in the future we have more sophisticated ways of using it. Okay, thank you very much.